In this videotape, we will learn how to simplify the form of a radical. A radical expression is said to be in simplest form if it has three special characteristics. Generally speaking, a radical that has been put into simplest form is easier to work with than one that hasn't. Although I want to warn you that sometimes when we put a radical into simplest form, the expression that we wind up with may look more complicated than the one we started with. The key is that it's usually easier to work with radicals that are in simplest form. For that reason, we're going to put them into simplest form. Now, the characteristics of simplest radical form are as follows. First of all, there are no perfect squares there are no perfect squares that are factors of the quantity under the square root sign. Okay, our radicals in elementary algebra are all square roots. We don't want there to be any perfect squares that are factors of the quantity under the square root sign. If there were, then we could pull something out. Okay, we'll see examples of this later on. Our general rule is that we would like to take out as much as we can from under the radical sign in order to simplify what's left under the radical sign. The second characteristic, there are no fractions under the radical sign. And finally, there are no radicals in the denominator. These are the three characteristics of a radical that is in simplest form. Okay, first of all, you've tried to take out as much as you can from under the radical sign. So you don't want any perfect squares as factors of the quantity under the radical sign. If there were, you could pull something else outside of the radical. You don't want any fractions under the radical sign and no radicals in the denominator of any fractions that might appear in the expression. Okay, now we have certain tools for putting a radical into simplest form. Okay, these were discussed in earlier videotapes. I just want to summarize them for you now. Okay, in what I'm writing now, A and B we'll consider to be two positive real numbers. Okay, we have the following properties of radicals, which will be helpful to us in putting a radical into simplest form. First of all, the square root of a product is equal to the product of the square roots of the factors. Once again, I'm reminding you that A and B are considered to be positive numbers here. The square root of the product, okay, of two numbers is equal to the product of the square roots of the numbers. Okay, secondly, the square root of a fraction, and B, of course, is not 0 because I've said it's a positive real number. Okay, the square root of a fraction is equal to the square root of the numerator divided by the square root of the denominator. The square root of a fraction can be broken up into the square root of the top over the square root of the bottom. And finally, we all know that the square root of a number times the square root of the same number is equal to just the number itself. The square root of A times the square root of A is equal to A. Now we're going to be using these properties in order to simplify the form of a radical. Okay, now let's try to put a radical into simplest form. We'll start with very simple radicals, say the square root of 20. Okay, we don't have to worry about any fractions under the radical sign here or any radicals in the denominator. The only thing we have to worry about is satisfying the first characteristic of simplest radical form, namely that there shouldn't be any perfect squares as factors of the quantity under the radical sign. Okay? In other words, there shouldn't be any perfect squares in 20. But of course, 20 does have a perfect square factor. 20 can be thought of as 4 times 5. The square root of 20 is equal to the square root of 4 times 5. And using the first property of radicals that I gave you over here, we know that the square root of AB is equal to the square root of A times the square root of B. So the square root of 4 times 5 would be equal to the square root of 4 times the square root of 5. Applying that over here, the square root of 4 times the square root of 5. And this 4, of course, is a perfect square. The square root, this is the positive square root of 4, is 2. This gives us 2 times the square root of 5. This radical, this 2 to the square root of 5, is in simplest radical form. Okay, there are no perfect squares that we can pull out of the radical here. What you're basically trying to do is look for factors. Okay, when you have a number 20, you're looking for factors, perfect square factors of 20. Okay, over 1. Okay, so we would look for 4. Is 4 a factor? Because it's 2 squared. And then 9, because it's 3 squared. And 16, because it's 4 squared, and so on. Trying in each case to pull out as much as we can from the quantity under the radical. Okay, now I just want to point out that we wrote 20 as 4 times 5. We also know that 20 is equal to 10 times 2. But that would not have helped us in this problem, because neither 10 nor 2 is a perfect square. Okay, so you just are not factoring it any old way. You are factoring, but you're looking for perfect square factors. It is true that 20 is 10 times 2, but that is of no use to us in trying to put this into simplest radical form. Also, 20 is equal to 16 plus 4. Okay, but that will not help us either in putting it into simplest radical form. Well, you may say, well, isn't 16 and 4, aren't they perfect squares? That's true. The square root of 20 is equal to the square root of 16 plus 4, but that is as far as we go. We cannot say that that's the square root of 16 and the square root of 4. This is not true. We are not allowed to go from this to this. Let's go back to our properties of radicals. We have the square root of a product is equal to the product of the square roots. The square root of a quotient is equal to the quotient of the square roots. It only works for products and quotients. It does not work for sums. It does not work for differences. Okay, only for multiplication and division, not for addition and subtraction. So if we go back over here, while this might be very nice, okay, it does not work. Here we have a sum. 20 is equal to 16 plus 4, but we cannot say the square root of 16 plus 4 is the square root of 16 plus the square root of 4. It only works for multiplication and division, not for addition or subtraction. Okay, if you tried to finish this up, you'd have the square root of 16 is 4. The square root of 4 is 2. You'd have 4 plus 2, which is 6. And 6 is certainly not the square root of 26. Is the square root of 36. Okay, it does not work this way. If you want another example to bring home the fact that this rule does not work for addition, let me show you the square root of, say you have the square root of 9 plus 16. This is not equal to the square root of 9 plus the square root of 16. Okay, on the one hand, the square root of 9, that's 3. The square root of 16 is 4. We get 7 on the right-hand side. On the left-hand side, the square root of 9 plus 16 is the square root of 25, which is 5. Okay, 5 is not equal to 7. We cannot break it up, okay, for addition. Only for multiplication and division, not for addition and subtraction. Okay, let's try to simplify the form of some more radicals. Okay, let's work with the square root of 108x cubed. Okay, throughout our work on radicals, we will assume that all variables are positive real numbers. The square root of 108x cubed, we would like to simplify the form of this radical. Okay, now we're looking for perfect square factors of 108. Now let's say you happen to be really sharp and you happen to notice that 36 is a factor of 108. And you say, well, I can rewrite this as 36x squared times 3x. Okay? This gives you 3 times 36, 108. X squared times x is, of course, x cubed. If you were able to see this on the first step, then you have the square root of a times b. You can make this the square root of a times the square root of b. And we have broken this up. This is a perfect square factor of 108x cubed. 36x squared is the largest perfect square factor that we could find. The square root of 36x squared is 6x. The square root of 36 is 6. The square root of x squared is x. Remember, we're assuming that x is positive here. And we get 6x times the square root of 3x. This is simplest radical form for this example. OK, now suppose you didn't know that 36 was a factor of 108. OK, you don't have to worry. You can approach this very systematically. You don't have to pull it all out on the first shot. OK, you know that you're looking for perfect square factors of 108, something over 1. So the first thing you might try would be 4. And 4 goes into 108. OK, and you say you have 4 times 27x cubed. OK, you're looking for perfect square factors, and you hit upon 4. And you say 4 times 27, that gives you 108. You can use your theorem. The square root of a product is the product of the square roots of the factors, this stage. The square root of 4 times the square root of 27x cubed. This will give us 2 times the square root of 27x cubed. Now, we're not in simplest radical form yet, but we're working with less under the radical than we started with. Okay, so you don't have to do the reduction all on one step. We're going to finish this problem off and see that we get the same answer. Okay, you don't have to do it all in one step. If you notice that 4 is a factor, you can pull that out and then go back for more later on. Okay, let's continue this problem over here. The square root of 108x cubed, I wrote it as 4 times 27x cubed. This is as far as we've gotten. 2 times the square root of 27x cubed. Now we look at 27x cubed and say, well, there's still perfect square factors of that. 27x cubed can be broken up into 9x squared times 3x. Okay, 9 is a perfect square factor of 27. And this step, I'm going to also take the x squared in with it. So we can make this the square root of 9x squared times the square root of 3x. This gives us now 9x squared is a perfect square factor. The square root of 9x squared is just 3x. And times the square root of 3x, giving us, as an answer, 6x times the square root of 3x, which is the same answer that we got over here. Okay, so we've done the same problem in 2 ways. We've gotten the same answer. If you're able to pull out the 36x cubed, x squared rather, on the first step, fine. This is what we did here. We noticed that the largest perfect square factor was 36x squared. We were left with the 3x. We broke it up. We got the answer right away. If you do not see that 36 is a factor of 108, you can do it bit by bit. You notice you're trying, of course, 4, 9, 16, like that. You're looking for perfect square factors. And then when you look at 27, you see that 9 is a factor, and so on. And you get the same answer. OK, let's try some more examples. The square root of 32 x to the 9th y squared. We want to put this into simplest radical form. If you want to try this on your own, you can shut off the videotape machine and come back for the answer. Okay, we're looking for perfect square factors of the quantity under the radical sign. Once again, we don't have any fractions in this particular problem, so we don't have to worry about the last two parts of simplest radical form. We'll come to that in a moment. We just want to master the first step, looking for perfect square factors of the quantity under the radical sign. Okay, now, perfect square factors of 32. I see that 4 is a factor, but 32, I'm also aware that 16 is a factor, and it's larger, and I may as well use that. I'm going to break this up and make this 16. Now, from x to the 9th, I'm going to take out x to the 8th. I could always take out the even power. Okay, the largest even power that's contained in the x to the 9th is x to the 8th, and then y squared, leaving me with 2x. This gives me 32 x to the 9th y squared. Okay. This is the square root of ab. I'm going to break it up, make it the square root of a times the square root of b. The square root of 16 x to the 8th y squared times the square root of 2x. Now, the square root of 16x to the 8th y squared, 16x to the 8th y squared is a perfect square. That's why we separated it out. First, you take the square root of 16, which is 4. Now, the square root of x to the 8th, the square root of x to an even power is x to 1/2 of that power. The square root of y to an even power is y to 1/2 of that power. Okay? If you were to square this, you would get 4 times 4, 16. X to the 4th times x to the 4th. You add the powers, you get x to the 8th. Y times y gives you y squared. So you have 4x to the 4th y times the square root of 2x. And this is now in simplest radical form. There are no other perfect square factors other than one that we could pull out here. Okay, now we're going to consider the square root of 5/4. For the first time, we have a fraction under the radical sign. If you remember our characteristics of simplest radical form, part 2 was that there should be no fractions under the radical sign. Okay? We're going to make use of the second property of radicals that I gave you, that the square root of a fraction is the square root of the numerator over the square root of the denominator. And in doing that, we see that we can write this as the square root of 5 over the square root of 4 is just 2. We now have this in simplest radical form. Okay, I'm not saying that there can't be any fractions in your final answer, only that there should be no fractions under the radical sign and no radicals in the denominator. You're allowed to have fractions. What's under the radical sign should be as simple as possible. There are no perfect square factors that we could take out to simplify this expression. Okay, there should be no fractions under the radical sign and no radicals in the denominator. So this qualifies for simplest radical form. Okay, let's look at 6 over the square root of 3. Okay, now we have a radical in the denominator. And the way we're going to handle the fact that we have a radical in the denominator, we had one over here too, but it was a very simple case because the radical in the denominator was the square root of a perfect square, and we were able to eliminate it on the first step. Okay, our object here is to get the radical out of the denominator. Since the square root of 3 is not the square root of a perfect square, we can't just write it without the radical on the first step. What we're going to do is make use of the fundamental principle of fractions that says it's perfectly okay to multiply the numerator and the denominator of a fraction by a non-zero quantity. You will get an equivalent fraction if you do that. Okay? You're allowed to multiply the numerator and the denominator of a fraction by a non-zero quantity, and that will give you an equivalent fraction. Now, what are we going to multiply by? We're going to multiply the numerator and the denominator by the square root of 3. Okay, this fraction is equivalent to this fraction by the fundamental principle of fractions. We've multiplied the top and the bottom by the same quantity. Okay, now, when you want to multiply two fractions, you multiply the tops and you divide by the product of the denominators. We have 6 times the square root of 3 on the top. On the bottom, we have the square root of 3 times the square root of 3, which is just 3. This is from your third property of radicals. If you'll remember, the square root of a times the square root of a was just a. The square root of 3 times the square root of 3 is just 3. Okay? 6 times the square root of 3 over 3, and we can simplify a little further. We can divide numerator and denominator by 3. 3 divided by 3 is 1. 6 divided by 3 is 2, giving us a final answer of 2 times the square root of 3. We now have that in simplest radical form. By the way, this procedure is known as rationalizing the denominator. Okay, since we have removed the radical from the denominator and replaced it by a rational number. Okay, let's try one more example. The square root of 2/5. This is going to combine the procedures that we've used in the last two examples. Okay, we have a fraction under the radical sign, so the first thing we're going to do is to say the square root of a fraction is the square root of the top over the square root of the bottom. Okay, in doing that, we find out we have a radical in the denominator. Okay, we are now going to rationalize the denominator. We are going to multiply numerator and denominator by of this fraction by the square root of 5. This will eliminate the radical from the denominator. Okay, we are multiplying the numerator and denominator by the same quantity, so we're going to get an equivalent fraction. On the top, we have the square root of 2 times the square root of 5, which we can write as the square root of 10, using the first property of radicals in the reversed order. Usually we say, before we were saying, say, the square root of 10 is the square root of 2 times the square root of 5. Now we're saying the square root of 2 times the square root of 5 is the square root of 10. The square root of 5 times the square root of 5 is just 5, using the third property of radicals. The square root of a times the square root of a is a. We have the square root of 10 over 5. We have now no fractions under the radical sign, no radicals in the denominator, and what is under the radical sign, namely 10, okay, is as simple as we can get it. There are no perfect square factors other than one that we could pull out to simplify this. Okay, and we now have this in simplest radical form. And that brings us to the end of the tape.